5, 4, 3, 2, 1.
Every year, space agencies announce new timelines for sending humans to Mars. Every year, those timelines get pushed back. And if you dig into the actual scientific data, not the press releases, but the real research papers that NASA and ESA quietly publish, you start to understand why. 4 reasons. 4 specific, peer-reviewed reasons why any human who travels to Mars faces conditions that are genuinely incompatible with coming home. None of them are secret. All of them are published. None of them make the headlines. Let's start before anyone sets foot on Mars. Let's start with landing. Mars has an atmosphere, about 1% the density of Earth's. And that 1% creates one of the most dangerous engineering problems in spaceflight. It is thin enough to be almost useless for slowing down a spacecraft, but thick enough to generate enormous heat through friction as you enter it. You need to slow down from 21,000 kilometers per hour to near zero in 7 minutes, on a planet where any signal you send takes over 3 minutes to arrive, and the response takes another 3 minutes to come back. Real-time control from Earth is physically impossible. Every Mars landing, rovers included, has been autonomous. The spacecraft lands itself, by itself, with no human able to intervene. This has worked for robots weighing a few hundred kilograms. A crewed Mars vehicle would need to land something 20 to 30 times heavier. We have never tested a system that can do this. As of 2026, no agency has a fully validated large-scale Mars landing system. SpaceX has a concept. NASA has concepts. None have been tested at Mars scale. The journey to Mars takes approximately 7 months. In deep space, outside the protective bubble of Earth's magnetic field. Earth's magnetic field is extraordinary. It deflects an enormous portion of the cosmic radiation that constantly bombards our solar system. Particles moving at near light speed from exploding stars across the galaxy. On the surface of Mars, there is nothing stopping it. NASA's Curiosity rover has a radiation detector on board. During the 253-day journey from Earth to Mars, it measured a radiation dose that would give a human being 0.66 sieverts. That is 66% of the total radiation limit NASA allows an astronaut over their entire career, in one trip. But the trip is just the beginning. Once on the surface, the radiation continues. Mars has no global magnetic field. Cosmic radiation reaches the surface directly. The cumulative dose from a full Mars mission. Transit there, 18 months on the surface. Transit back, is estimated at 1.01 sieverts. That increases lifetime cancer risk by approximately 5%. Which sounds manageable, until you account for solar particle events. Sudden bursts of high-energy radiation from solar flares that can deliver a lethal dose in hours, with no warning. In 1972, between Apollo 16 and Apollo 17, the Sun released one of the largest solar particle events ever recorded. If an astronaut had been walking on the Moon or in deep space transit to Mars, the radiation would have been fatal within days. There was no warning. There was no way to predict it. And this is not a theoretical risk. NASA tracks solar activity constantly using the GOES satellite network. But prediction models for solar particle events are still limited to roughly 15 to 30 minutes of warning. On Earth, that is enough time to take shelter. On a spacecraft between Earth and Mars, 15 minutes may be the difference between mild radiation sickness and a fatal dose. The Mars crew would have a storm shelter, a heavily shielded compartment at the center of the spacecraft, surrounded by water tanks and equipment. Water is one of the best radiation shields available. The crew would retreat there and wait, for hours, possibly days, in a space roughly the size of a large closet, together. Mars has an atmosphere, and it is lethal in 3 distinct ways. First, it is 95% carbon dioxide. A single breath without a spacesuit would begin killing you not from lack of oxygen, but from CO2 toxicity within minutes. Loss of consciousness, death. Your suit is not a luxury on Mars. It is the only thing between you and death at all times. Second, the atmospheric pressure on Mars is 0.6% of Earth's at sea level. At that pressure, the boiling point of water drops to approximately 2 degrees Celsius. Your blood, which is largely water, would begin to boil, not from heat, from the absence of pressure. The technical term is ebulism. It begins within 15 seconds of suit failure. Third, dust. From Mars Reconnaissance Orbiter, before and after. Mars has global dust storms that can last for months and cover the entire planet. The 2018 dust storm killed the Opportunity rover by blocking its solar panels for weeks. A crewed mission dependent on solar power during a global dust storm faces potential mission failure. And this dust is not like Earth dust. Martian dust contains perchlorates, toxic compounds that interfere with thyroid function. If any significant quantity is carried into a habitat on a spacesuit and inhaled over months, the health consequences are serious and not fully characterized. All of the physical challenges assume one thing that is itself not guaranteed: that the crew's mental health survives the mission. The longest single continuous period any human has spent in space is 437 days. A Mars mission could last 900 days. More than twice as long, in a confined vehicle with the same 4 to 6 people, with a communication delay that makes a conversation with Earth take 20 to 40 minutes round trip. NASA's isolation studies show predictable patterns: interpersonal conflict, psychological withdrawal, and what researchers call third quarter phenomenon, a significant drop in crew morale and performance around the 3-quarter mark of any long mission. On a Mars mission, the third quarter would be 675 days in. Far from Earth, unable to communicate in real time, unable to leave, and still months from the return window, NASA ran a study called High Seas, Hawaii Space Exploration Analog and Simulation. 6 crews, isolated in a dome on a Hawaiian volcano for periods of 4 to 12 months. Mars-like terrain, communication delays simulated, no real-time contact with the outside world. The findings were consistent across every mission. By month 6, crew members reported that small irritations had become major conflicts. Noises, habits, the way someone chewed their food. Things that would be trivial in normal life became genuinely difficult to tolerate. One crew member described it as, you run out of things to talk about around month 3, and then you have 3 more months of silence with the same people. On a Mars mission, that would be month 3 of 22. Going to Mars doesn't guarantee you never come back, but it requires you to accept cumulative risks that stack on top of each other. in ways that no Earth-based simulation has fully replicated. The people who will eventually go to Mars will know all of this. They will go anyway, and that is, depending on how you look at it, either the most admirable or the most terrifying thing about the human species. Space is far stranger and far more hostile than most people realize. From impossible planets and deep space missions to unexplained phenomena and the mysteries still hidden beyond Earth, this is only the beginning. Subscribe for the next journey